Hello guys, in this video I'm going to talk about the beauty of the normal density function or the Gaussian density function. So first let me introduce you to the normal density function, and then we will see where can we use this in our course of pattern recognition. So normal density function or Gaussian distribution can be compared analogous with the sphere or circle in shapes. So if we see around, we see say the solar system, we go we go in the outer space. So we model every planet or stars as spheres, even though they may be ellipse or they may be something very different, but it is very similar to sphere, and the calculations uh, with respect to sphere are easier. It has only one parameter, the radius, and you can find the volume or whatever things that you want. So whenever we talk about these things, we see what is most common or most similar in nature, and then we see how many parameters that does it want. So similarly, a Gaussian distribution is like, it is very good approximation for most of the random variables of the natural case. So um, say if it is very common in nature is what happens with Gaussian density. uh, it is again an approximation. You don't say that every natural process tends to Gaussian distribution, but it is a good approximation. Like, not every planet is sphere. In fact, I guess none of the planets are sphere. But then the sphere is a good approximation for the planets. The same thing is used over here. Plus, here with Gaussian, we just have two parameters, mu and sigma square. So mu is the mean of the Gaussian distribution and sigma square is the variance. So just if we know the mean and the variance, that's it. We know the distribution. That is what it essentially means. So if you see the formula of the Gaussian distribution, you see there are only two terms that are unknown, or basically sigma square or mu. So this mu will decide where will be the center of the Gaussian distribution, and the sigma square will decide its spread. So here mu minus sigma and mu plus sigma will always cover 68.2% of the total area of the Gaussian curve, and mu plus 2 sigma, mu minus 2 sigma will always cover 95%. So if sigma is smaller, we will see this graphically also in Desmos. I will show you how Gaussian distribution changes when we change mu and sigma. So just hold on for that. In a minute I will show you that. So that is the important parameter, and you know the distribution, that is all. So this is the beauty of the Gaussian distribution. So if here on the x-axis I have the random variable, so if this random variable follows a Gaussian distribution, so I'll write the p of x. The p of x follows a random distribution. So that is what I have mentioned over here. So where will we use this in our course? So remember, in the first lecture I talked about likelihood. So I talked that likelihood is generated from the training sample, training data. So we are basically making the machine learn that, say, given we have two different sets or two different classes of data, so we want to make the computer learn that, see, this particular image or this particular pattern, if you encounter, it is a sunflower, and then if this particular pattern if you encounter, then it is a rose. This is what we want the computer to learn. So what we are doing is, we are going to approximate this PDF. Remember, I had told that this is continuous, so it is a density function. So we are going to approximate this as the Gaussian function or the Gaussian distribution over here. So we are going to take a special case that our likelihood is a Gaussian distribution. Now this may or may not be true. You can put any distribution over here, but for the case of starting, so we are just starting the course, and we are new to this course, so we are starting with the Gaussian distribution. So we'll assume that our likelihood follows Gaussian distribution. So what does that mean? That means that if suppose I am given with say 100 samples or 100 images of sunflower, I've been given 100 images of sunflower, and I calculate, say for first image, what is the length of the or the size of the object. So we were calculating the radius. So I will calculate what is the radius for the first image. So let this radius be 5. So for the first image I got the radius as 5. For the second image I got radius as say 6. For the third image I got this. So remember, this can take continuous value, so I can get say 3.5. For the next I got say some 2. So this can be a quite variation. I can have many different types of sunflowers. So next what I'll do is that I will see that what is the mean of these particular samples. So we can take the mean of out of these samples. I will in my future videos I will prove how can we calculate the mean and the variance. So that comes under parameter estimation, which I'm going to upload. My few next videos will be on that. So but for understanding now, we can take the mean of these samples and by that compute this mean, the mu. And similarly, using statistics we can compute the variance of these samples, and we can compute the standard deviation of the variance, and we can compute the sigma. So in our case what is happening is, in our case we are given that it is a sunflower, it is given that these are the images of sunflower, so it is given, and we are seeing that what is the probability of the different x's of different x's. So here we saw we got an x is equal to 5, we got x is equal to 6, 3.5, etc. So we are seeing that on the x-axis, and given that it is sunflower, what is the probability distribution? That is what we are doing. So this becomes the likelihood of sunflower. Similarly, I can define a likelihood for the rose. So let this be the random variable x. It is denoting the size or the radius in our case. So this is the random variable, and I am plotting all the omega I. So we denoted these different sunflower roses as omega 1 and omega 2. So sunflower was omega 1, so let this be omega 1 and this be omega 2, right? Sunflower is omega 1, rose is omega 2. So what we essentially are doing is, we are first say sort of calculating the mean, as getting the mean, so that I will say as say mu1. So the mean of all the training data we have, we calculated the size of each and every this sunflower of the images that we had, and we calculated this mu1. Similarly, we calculated the mean of all the sizes of this rows that we have, and we got mu2. So sunflower will be normally bigger, so let me put mu1 over here. So mu1 will be quite bigger, and let mu2 be over here. So intuitively roses are smaller than sunflower. That is an assumption. So basically it is just an assumption. So mu2 comes over here, and mu1 comes over here. One sec. Mu1 is sunflower, right? So let mu2 come over here. So I am just assuming that roses will have a lesser mean, and here similarly I can find out the covariance or the variance, sorry I'm mistaken, the variance of these and find the sigma. So I can plot two curves now. This will belong to probability that the given that I have sunflower. So for these images, so no, we took this as rows, right? So given that I have these so many samples of rows, the probability of x, so given that these are the sample of rows, the probability that the size will be any x, it can be 2, 3, 4, 5, 6, is given by this Gaussian. And given that this is the data of sunflowers, I can calculate the probability of the different x of the sunflowers. So like this, we are basically visualizing both the probabilities as a function of x. Now this is what we do in the training set. So the training data, or the training of the algorithm, essentially gives us these parameters mu1, mu2, and the variance. So there will be some variance sigma 2 and sigma 1. So that is what we get from training, and we find out these things. So now this was about the likelihood. So we essentially want this. For when we'll test our data, we want this. What is the probability that I have been given? Now in the testing, what will happen, I will be given an image, and any image, it may not be from this data, any image of rows, and I will be able to extract the size of that rows, and I will have the value of x, and then I will find out, chalo, tell me, is this image a sunflower image or a rose image? And we are doing that by using this length. So we are calculating, say, the given image is having length, say, x is equal to 2. This is the test that we are talking about, testing. So the given image is having x is equal to 2. So we'll calculate the probability that it is sunflower. So here, let me take an instance where x is equal to 2. So say here x is equal to 1, and say okay, let this be 2. So this is, say, x is equal to 2, this is 3, 4, 5, 6, and the story. So I have got an image where the x is equal to 2 over here. So my that image lies at the point, it lies over here. So now let me see, this probability of it being rose is greater, and the probability of it being the sunflower is less. Okay, there may be a question that this is a PDF, it is a continuous plot. So for continuous plot, the point probabilities are 0 actually. But here, since we are not only using the prior, but we are also using the not only using the likelihood, but also the prior and the evidence. So here, this P is actually what we take. We don't consider it as 0, we take the function as it is where it is. So we will take, say, x2 is equal to here, so this likelihood is this thing, and for this for it being a sunflower, the likelihood is this. So you can see evidently that it has a greater probability of being rose, so we assign it as rose, the decision rule that we saw. So this is what is happening. Now if suppose we have some so we'll obviously have some prior information, that how many images do we have, or how, which is more common, or etc. So that will get multiplied with the likelihood. So say the prior for rows is say prior for rows is say 0.3, and prior for sunflower is a 0.7. So then these things will weight this likelihood. So what will happen is, this 0.7 will get multiplied by this, so this will get a little smaller. It is multiplied by 0.7, so this will go. So this became a little solved because we now considered the prior, and now this is not the likelihood, but it has now become the posterior. So it has now become this. So we saw that we are mostly ignoring this evidence term. So we just took the likelihood, multiplied it with the prior, and we got our posterior. So that this is what we have over here. We have our posterior. So similarly, this rows will get multiplied by 0.3. So this will further get reduced. It will be somewhat like this. So this will no longer be the likelihood of rows. Now it becomes the posterior for rows. So please understand these notations, how I am going from year to year. Initially we plotted this, we multiplied it with the prior, and we got the posterior. And we are always in the decision rule, we are always comparing the posteriors, right? We are not comparing the priors. We are always comparing posteriors, that is omega 1 is in the numerator, right? So by this we get this, and now we are comparing, say x is equal to 2, my given image, test image has x is equal to 2. So we'll compare where does it lie, which probability is higher. So here you can see the probability of rows is higher, so it will assign it to rows. If suppose I take a function, say x is equal to 3.5, so I got an image whose x is equal to 3.5, so it will lie over here. So the probability of it being a sunflower is more, this is for sunflower, than the probability of it being rose. So it will assign sunflower. So here you can see there is a point where both the probabilities are the same. So this is a sort of a discriminator, right? So any point, so let this be some discriminator, so it is discriminating the probabilities. So any point that is before this will always be classified as rows. Any point that is after this will be classified as sunflower. So there will be some discriminator, say x is equal to this is 2, say x is equal to 2.8. So using the training data and then finding the posterior probabilities of both, we found out a line. This line tells me, this line is x is equal to 2.8. so this line tells me if the given image in the test, if the given image will have any size that is less than 2.8, I will classify it as rows. If it has any size greater than 2.8, then I will classify it as sunflower. So this is what we are doing in Bayesian decision rule. So the significance of this discriminator is a lot. This is the thresholding sort of thing that we are doing to discriminate that a given image or a given data is belonging to a particular class or it is belonging to the other class. So now let us quickly go to Desmos and see how mu and sigma variations give the change of the shape of the Gaussian. Let us see that. Right, so I'm in Desmos here. So I have plotted the Gaussian distribution over here. So this is the Gaussian distribution. Let me explain you the parameters. So 1 upon 2 pi sigma square half e raised to, oh, there should be a square over here. So yeah. So 1 upon 2 pi sigma square raised to half, so there is a root e raised to minus x minus mu upon 2 sigma square. So this is the Gaussian distribution formula, and here A is the mean. So you can see when this is A, so when I move the mean, so it is just moving the Gaussian from here to there. So the center, if A is equal to 1, you see the Gaussian distribution centers at 1. That is an important thing to note over here. Next thing is that so when you move B, when you change B, you can see that the width of the curve changes. So when B is very less, say 0.2, it is a very narrow curve. So B of 0.2 means that lot of area will come inside this. So remember I said mu plus sigma, mu minus sigma, so that should have 65% of the area. So that will signify this. As you increase this, the variance starts to increase and then the area starts to spread. So that is the beauty of variance that you can see over here. So now what I have done here is this is my likelihood, as I mentioned before, and this P1, let P1 be the prior. So I am denoting this red graph as the posterior for rows. So the posterior of rows will be basically its likelihood into its prior, right? And now there is this new Gaussian function. This Gaussian function I am going to denote by yellow. So this is for sunflower, and here this is the likelihood of sunflower and this is the prior. So basically here I am considering a two-class case. So the prior and the prior will just be 1 minus. If this is 0.3, this will be 0.7, because there are only two cases, right? So that is what we can see over here. I can also vary the mean and variance of this sunflower. So I have the mean and variance of sunflower over here. So by some data, the training data, I can fix the value of mean and variance. So let us say we will stick to our example. So we saw that in our example I had rows somewhere between here 2, and I had this somewhere, say over here, say take it anywhere, say I am taking it, say 3 is okay I guess, and let us change the variance also a bit. So let me take this as the variance. So a rows will have, say mean size, a mean radius of 2, and it's varying from say 0.1 for small rows and up till say 4. And for so these are random values that I am taking over here just to explain you. And let me take sunflower or something like this, say it has something like this. So now it is it is little difficult to observe this. So what I'm going to do is I'm going to remove the scaling factor. So it will not matter anything because I'm removing the scaling factor from both. So it will not matter much if you see. So yeah, so you saw this point, this there was this point over here, this some point over here. So it is still, so whenever I put this point is still over here, and when I remove this from both, it is important to remove from both, I still see this over here. So it is more or less, because we are comparing two things, so the scalars and the evidence that we saw is not, it does not really matter. So let us see this kind of distribution. So now currently I have kept the prior as 0.5. So prior is the same. So let me define a discriminant. So this is a kind of a discriminator that I was talking about. So here in the test sample, I can get any value of x over here. So yeah, I can take any value of x. So its corresponding intersection with these posteriors will tell me its posterior probabilities. So as I had taken an example of x is equal to 2, so I get an image. I'm getting an image with the size of that particular image feature vector, b x is equal to 2. So then this will be that image, the test data. So here the probability of the posterior of it being a sunflower is this, and it being a rose is this. So hence this will be defined as rose. So the algorithm will make it rose. So like this, you can see it is this point, the intersection of two, where the probabilities are equal basically. So if there is any sample before this discriminator, then it will be always categorized as rose. If it is a point which is after this discriminator, then that will be categorized as sunflower. So this decision rule gives me this particular discrimination, and we are going to talk about this discrimination function mathematically also, but I wanted to show a visual representation of it. Also here if I change the prior, so if I'm changing say like this the prior, so now here I am giving more priority to rows. So I am assigning, so rows is becoming this into 0.7, so it is enhancing, and because of this the sunflower is going down. So when I change the prior, you see that my discrimination boundary changes. So now my discrimination boundary has come over here. So initially it was say here, now it has come to here, you see. So it is the prior and the likelihood both that determine our discrimination boundary. And what is our discrimination boundary? It basically tells you the region of sunflower and the region of rose. So this will be the region of sunflower. Any sample which will have radius or size greater than this particular value will be sunflower, and less than this value will be rose. So we are going to see discriminant functions in detail in the next lecture, coming lectures. So here I have shown Gaussian distribution with only one variable, only one x, but then we saw that we could have many features. We could have 2 features, 3 features. So we are going to see a multivariate Gaussian distribution also in my future uploads. So there also I'll try to graphically show you how things are happening using a 3D graph plot. So please stay tuned. There's a lot of nice visual content that is going to come, and thank you so much for watching. Thank you so much.